Hello, everyone. All right. I think the live stream should be working. As always, we'll double check. Looks like I can see that it's live. Cool. Oh boy, I think the title's wrong. Was the title changed from our generic message? Twitch TV pwn.college. Let's see here. Yeah, that's not right. How do I fix that? Settings. Robert, you just had to change it. Well, hopefully mod view doesn't do something weird. This. I'm just going to change it back to the nice generic message. Learn to hack. That? Yeah, we'll call it that. I don't remember what it used to be. Learn to hack sounds cool. Cool. Is that fixed now? Why no one looks at that thing anyways, but just to make it even clearer. Yeah, it looks like it's fixed. Okay, cool. All right, this week we are on the building a web server module. And of course, as always, if there's ever questions throughout this, feel free to ask in the Twitch chat, and I will address your question to the best of my ability. Current module is due in 7 days, 12 hours, and 54 minutes. So be here before you know it. This module, we're on the third module. It is a kind of culmination of the first two modules. So the first module, we were an HTTP client. The second module, we wrote x86-64 assembly. And on this module, we are the web server, and the web server written in x86-64 assembly. So yeah, that's what we're doing here. At the end of this all, you should have a web server that, let's see here, can respond. So if I write, let's see, a little example, new terminal in editor area. Let's see if we can do that. It's not very good though. That. Clear. Okay. And if I pretend this is my web server. So right now I'm just going to use netcat. My netcat is not my web server, but we're going to pretend it's my web server for right now. And I listen up on port 80. And VS Code detects that, of course. And I say curl localhost 80, right? My web server that I'm writing in assembly is getting this piece of data. So we've got to first handle this logic of listen on port 80. This is going to take 4 system calls. We talk about those 4 system calls here. Okay, we got socket, we got bind, we got listen, we got accept. Those 4 system calls you're going to make sequentially. And in doing so, you're going to accept, and you're going to be able to, as this lecture video talks about, you're going to accept, and suddenly you're going to receive a connection. Right? If we switch over here, I think, we accept this comes in. And I mean, I guess in this case, we're not doing a read. But if you wanted to parse this thing, you're going to read whatever data comes in. And we'll show this in this office hours a little bit in a different context. But this data is just coming in. You could pretend this data is coming in over standard input for all we care. Now, technically, it's coming in over the network because a good web server operates over the network. But you could have your web server operating over files or over pipes or over other things. It could just literally be typing by hand web requests, as you did in Module 1, but just in a non-network context. Now we just need to parse this thing. In this case, we're going to send a very simple reply, right? Curl is currently stuck. It's waiting. We don't see a new $sign space because it's waiting for this command to finish. Curl hasn't received its HTTP response, so it's just sitting here waiting. If I give it an HTTP response, HTTP 1.1 200 OK. This is like the simplest possible response we could give. We just say, sounds good, right? It's like kind of do nothing. We're not saying there's any errors. We're just saying, yep, okay, cool. There's no reason we can't return this. And if we do this, why is this going down? Hold on, what's going on here? Oh, we had to, I see. So we'll do it again. Curl local, netcat, listen, curl. This comes in. We say HTTP 1.1, so 1.1 200. Okay. And then we're going to send Control D to say, hey, we're not sending anything anymore. / maybe Control C. And this comes back, right? It is totally cool. If we wanted to actually include some sort of response, right? This is just an empty response. That was fine. If we look at this, right, with -v, well, we failed there. If we netcat listen, if we curl -v, right, we can see it sent this. We obviously agree because we're looking at the server as well, that it sent that. And if I say HTTP 1.1 200 OK, right, we got it, okay. If we want to instead make output appear without this -v thing, right, we want to show something up on the screen. We could do that. How would we do that? Well, we curl. We say HTTP 1.1 200 OK. We say content length 4, for example. So this means I'm going to have a response that's 4 bytes long. And I will send ABCD. And you'll see it actually ends this time. And we get curl localhost 80. And the response we get is ABCD because 4 bytes. If we set this up again, you could imagine testing the bounds of this whole process. We could say HTTP 1.1 200 OK. We could say content length 2. And then we could say ABCDEFGHI. We'll see what happens. I really don't know how curl is going to respond to this. Yeah, see, we only get 2 bytes of it. Curl really respects that content length. And so it says 2 bytes. 2 bytes came back. And this is pretty much more or less the module. It's just, instead of sending these arbitrary responses, you're going to be paying attention to this path thing. As we get later into the module, you'll pay attention to this path thing. You're going to parse this thing a little bit. Really, you just need to figure out what the heck this is. And if something is sent that is going to be some sort of file path, for example, you're going to open that file, read it up, and send the contents of that. That's really all this module is. That and getting very familiar with making system calls. Got a hello chat. Sweet. Okay. So that is the basic idea of making requests. Now, I'm not going to do a super deep dive into building this thing out, right? The lecture video goes pretty in depth of how you build a web server. And if I sat here and wrote all the assembly, well, now you'd have the solutions for all of the modules, which is no fun. So instead, what we're going to do is we're going to implement a different program. We're not going to pay too much attention to this networking stuff because, again, the lecture videos tell you how to make all of these networking system calls. Instead of going over file descriptor 4, which is our networked connection that came back from accept, we're just going to go over file descriptor 0. And instead of HTTP, we're going to do something else. We're going to have our own language. Are we going to have our own language? No, we might not have our own language. We're going to implement a shell. That's what we're going to implement. So right now we have, and believe it or not, they're not so unrelated. I mean, they're pretty unrelated, but what it looks like to build them is very similar. So we're talking about a web server. In this case, I have a program that's reading over standard input. The very first thing it does before it reads over standard input, though, is it just prints $space, right? This program just does that. And then I type something like, who am I? And it knows how to print hacker. And then I type something like, let's see here, ls/flag, and it prints /flag. Whereas if I do ls/hello, it says ls cannot access hello, no such file or directory, right? This is just a back and forth of input and output. And this is just a bunch of system calls that is making this happen. It's really not so dissimilar from your web server that you're going to be building. It's just, we're not necessarily parsing HTTP. Instead, we're parsing this like space separated command, right? We've got like ls, which is like the program we want to run, and then we've got some argument passed. We might have multiple arguments passed, right? We might say like this program, this argument -al, and then this argument. So argument 1 or argv0, argv1, argv2. This ends up kind of being argv0. And that induces a slightly different behavior, right? Because the ls program can take flags. And so it is able to do slightly different things. If I just do ls-l, well, I guess it's not going to make a difference here. This is going to do the same thing. The A specifically allows you to see hidden files. But I could also, for example, ls/flag, and this is going to be slightly different. Rather than just setting up arguments, you do ls-l/flag greater than temp hello, right? And now it doesn't print anything to the screen. Instead, what it did, and we can write just another space-separated command, and we'll see that now the contents of this is in this file here, right? This all is just standard in, standard out, standard in, standard out, standard in, standard out. And it's just responding to what the user said and doing something in a well-defined way. And then it's not just like space-separated arguments. This language has more intricacies to it. And this language can get even more complex and more complex. There's more and more features. This basic idea of just starting a program and printing it out is pretty straightforward. One layer up maybe, right, is the ability to add this feature to parse. Somehow you parse this thing and you figure out that we got this somewhere in here. And now we got to like deal with this. Right? You can make a slightly simpler language. Maybe you say, because this is also technically valid bash, we don't need a space here. Maybe this is easier to parse. We just say, okay, well, if any of these arguments like if the last argument starts with a greater than, like don't put it on standard out, put it in the contents of whatever the heck is specified here, right? You could like simplify this language. Technically the specification allows for much more, but you could simplify this language and say this is the requirements now for my program that I'm writing. That's how I'm going to respond to user input that I receive. I'm going to act on that. And the way that we do that is it's just a bunch of system calls. So let's go ahead and do that. So let's go, we'll remove that core file, 5, make dir, we'll just make dir shell, cd shell, and we'll copy assembly makefile here, and we'll copy assembly test.s to here. Cool. And then we don't really care about this anymore. We don't care about that anymore. We don't care, we don't care, we don't care. Now let's open up this test.s file. We'll get rid of almost all of this. We don't really care about that. And let's start writing this program, right? Writing the shell. It's not going to be bash. It's going to be R shell, much simpler version, but the ideas are still there. The very first thing we need to do is we need to print $space, because that's what our shell does, is it prompts us with $space. So let's define some data. So we'll say .section, .data, and we'll say prompt. And I think we do that. Our prompt is $space, right? We just need to print this to standard out, so print this to the screen. So let's start with, let's also edit our make file. We'll make this debug option, not the default. And we'll need this if we decide to use GDB. Right now we're not using GDB. Hopefully we don't make mistakes. We'll use strace as our debugging tool, as we'll see. So we're just going to assemble it and link it, and then we'll run it. Okay. So we make, well, it doesn't like something. Oh, it wants a new line character. We make, okay, we assembled it, we linked it. Now we run it and we crash. Why do we crash? Well, we crash because, as we talked about at the very beginning of our introduction to assembly, we're not doing anything. And it's just falling off into those null byte instructions, and those null byte instructions crash. If we want to not crash, we can just throw an exit at the end. So if we look at syscall.sh, we will see we have our exit system call, as we talked about in class last week. You can make system call 60. The way you make system call 60, as a reminder, move RAX 60, that means give me the 60th syscall and syscall. And if we specifically want to exit with error code 0, which means no error, we move that into RDI. Move RDI is 0. Hopefully this is familiar. If not, say something in chat and I will do another explanation of that. But we've covered that a couple of times now. The first argument goes into RDI. The selected syscall goes into RAX. And this is just the behavior of the exit system call. It's this, can I do exit 0? If I assemble this, will that assemble? Sweet, we'll do that. So this doesn't work, right? Oh, it does work. Does that not work? Is that what I'm used to? Maybe that does work. Okay, we'll do that. Cool. So we just did exit 0. And we make this program, we run this program, and now it doesn't crash. It doesn't print out our $space. Well, our current shell does. You know what? Instead of $space, our shell is going to be fancy. It's going to do greater than space, just to show that we're a different shell. or maybe we want to be the, yeah, no, we'll do that. We'll be this cool little symbol. If we make this program and we run it, it doesn't print that out, but it does, if we strace it, it does call exit 0. So we can see it makes a system call exit 0 and it exits. Before we exit, we want to print out our prompts. So our prompts, how do we do that? Well, what we want to do is we want to write to standard out, so file descriptor 1. We want to write the address of prompt, and then we want to do 2 bytes, right? 2 bytes because this thing is 2 bytes long. Really, it's star length of prompt, but we'll just hard code it to 2. So how do we write? Well, the write system call is number1, syscall number1. So move rax1, set up our first arguments, our file descriptor. If we want to write to standard output, again, standard output is defined to be file descriptor 1, just by convention. File descriptor 1 is pointing when our program starts up to this visual display that you see here. Move RDI1, move RSI. Well, we want to put the address of prompt here. How do we do that? Offset prompt. Okay, again, this offset thing, a little bit confusing. This has to do with our assembler and our linker, that it just figures out how to put the right address there with this syntax. And then move RDX, our third argument is RDX. How many bytes do we want to write? We want to write 2 bytes. And then syscall, right? So we just write these, we fill in syscall number, fill in our arguments, make a syscall. Specify our syscall number, fill in our arguments, make a syscall. It's just that over and over and over. And sometimes you have little control flow mechanisms in your assembly that you're not just only making system calls. You want to do something maybe interesting, make system calls in response to something. But this, in the syscall world, is just fill in our arguments, make the system call. So let's do that. We will run it. And what do we see? $ space, and then our program exited after here. And then $ space, because now we're back in our original shell. So it's kind of maybe a little bit confusing because we kind of got a shell within a shell. Now maybe you don't say this is a shell yet, but we're getting there. The next thing we need to do, so we write our little prompt. The next thing we need to do is receive input. The way that we receive input is we read. And rather than writing to standard output to produce output, we read from standard input. So standard output is file descriptor 1. Standard input is file descriptor 0. It's just, that's the specification. So we want to read, so syscall number 0, so move RAX 0, move RDI 0, move RSI, well, we're reading something. We need to read some number of bytes. So, and these bytes are going to end up in memory. So here's where we have to make a design decision. We have to do some sort of thought process here. The read system call asks you, how many bytes do you want to read? Now, the simple implementation, I guess we'll deal with RSI in a second. Where do we want to read? The simple implementation for how many bytes do we want to read is to just say 100. And if we just say 100 and leave it at that, that means that someone can type a command that is up to 100 bytes long, 100 characters long, and that's just a limitation of our program. That's all we support, and leave it at that. You get 100 bytes. If your command takes more than that, too bad. Our shell does not support that. You could easily increase it. You just say, okay, we'll add another 0. Now we can take 1,000 bytes. And now we just need to find a place for 1,000 bytes to go and live. We can create our spot for something to go and live. So we could say command. And let's see here. What is the syntax for this? We basically want to say command is just allocate 1,000 bytes. Can we do db? No, let's write a byte. Let's see. Gas syntax allocate 1000 byte buffer. Is it array? Can you do array byte? Byte 10, byte 20. Oh, I guess this is saying let's try it. Well, what's small array is just a name. Yeah. Let's do byte 10 0 or something, like 10 null bytes. Does that work? Let's see. No, it doesn't really like that. I'm pretty sure I do byte 10. That's just putting a 10 there. Well, we also have that issue. I'm skeptical about that one. I think that's just writing a 10 byte. How do we make some space for ourselves? Use dupe. The heck is dupe? Equal to 0. All right, we'll try it. We'll try it. Dupe 20 of these things. I don't think that's it. Gas syntax for arrays buffers. So there's another solution to this problem, but I feel like we should be able to do this. All right, here's the real answer on how to figure this out. Yeah, in gas, how do we .lcom? .lcom. Expression, name 1, expression optionally named 2. lcom buffer 5120. This can refer to 5K storage. Okay, well that sounds pretty promising. With local uninitialized data. LC section. What the heck is the LC section? Not familiar with the LC section. Let's see if this works though. Is this like an older name for the BSS? lcom. And we'll say, well, but this is, hold on. This is giving it a name of buffer. Either way, let's test it. Buffer 100 bytes. Well, it did assemble. Worked for me. Okay. Not sure, but worked for All right, that's fair enough. All right, I'm kind of curious here. I'm going to do the real way that I would figure this out these days. ChatGPT. How do I allocate 100 byte buffer in gas Intel syntax blah? This is saying the .bss. Is that just the same thing as .lcom? Oh, space 100. All right, I think we don't need to necessarily do a BSS. Technically, a BSS is the correct thing, but we'll just initialize to null bytes. We're not going to deal with the BSS right now. For those, I guess, real quick, for those familiar or unfamiliar with the BSS, which I assume is most people, to be fair, we have this multiple sections. So right here, we're technically starting out, it's implicit, we're starting out in section .text. This is a chunk of memory where all of our code's going to live. Then we have section .data, and this is where, as the name implies, less confusing than text, this is where a bunch of data lives. But you can see like it's initialized data. It starts out with some values, and this is actually stored in the program that you run and gets loaded into memory. So the bytes responsible for this are going to get loaded into memory. Technically, the .bss section, so it would be .section.bss, this thing right here is allocated space for your program, but it doesn't go in the ELF. And the reason it doesn't go in the ELF, the actual program on disk, is it's an optimization where we're just going to initialize all of this storage you want to a bunch of null bytes. And it feels like if we want to request 10,000 bytes of uninitialized data, it feels like a waste to just put 10,000 null bytes into our program. Because why do that when instead you could just say, and I want 10,000 bytes reserved, which is exactly what the .bss is it says, I mean, it's going to compute the total length that it needs. It's just going to say, and I need 1,000 bytes. Give me the space for that. So it's just an optimization. So we're not going to deal with that optimization right now unless things yell at us. So let's try this command. And we'll say .space 1,000. I'm guessing this is gonna, we'll see what happens. Oh, well, we got our classic error. Make, well, it likes it. Kind of curious. I'm guessing we're gonna see so this is our greater than space, and then yeah, you'll see the way this works. Well, is that 1,000? Yeah, it could be 1,000 bytes. It's just putting 1,000 null bytes in here, I believe. I believe that we're responsible for this, I think. And so we just made space for 1,000 bytes. I think that worked. Yes, feel free to ask questions. Don't have to say like a specific level, but if you have a conceptual question that you're stuck on, please feel free to ask about it. Okay. Because believe it or not, this is something you have to deal with in the web server. You need to, you're going to realize at one of the levels, you're going to need space for yourself. You have a whole bunch of options. Do whatever you want to do. You can use the stack. So you can just refer to RSP as your location of memory where you're just going to start storing things because that is already initialized memory and you don't really care about anything. If you're not making function calls, you just let it chill and just use the space, the entire stack as your scratch space. In this case, we're going to try this approach of allocating 1,000 bytes for ourselves. So if we want to read, we specified syscall 0, file descriptor 0, standard input. We still needed to do RSI, so we'll do offset command instead. This is where we're going to read. We're going to read into memory to this location. 1,000 bytes, syscall. So what did we just do right here? Read 0, address of command. Maybe it's even clearer if I say input. Right, let's rename this to input. Or even input buffer. Right, real clear, hopefully. I don't know what's clearer to you, but call it input buffer even. 1,000. And so now we can support up to 1,000 byte inputs. Okay. And there's solutions to arbitrary length. If you really want to support an arbitrary length, you can make it happen. We're just doing a simpler approach where we're saying you get 1,000. Okay, so we make it, we run it, and now you can see we don't have our $sign space. Now we've got greater than space, and I can start typing. And then I hit enter and the program ends because, well, we don't have any looping mechanism. You want it to not end? Well, it's very simple to make it not end. We just say loop Don't loop. It's that simple. Now their program is never going to end. Make test hello. Wow, cool. This is another command. Except my commands don't do anything because I didn't parse the input buffer to do something, right? This is the program we wrote. If you want to make it so that it responds to something, right? In this shell, we can type who am I and it says hacker. Well, we can support that. Here's the very simple way to support that. Let's do another write. I'm going to just copy this logic. And instead of prompts, this is 3, 4, 5, 6. We want a null new line character also. 3, 4, 5, 6, 7 bytes long. 7 bytes, boom. And guess what? We run this program, and I type who am I? It works. Type who am I? It works. Fortunately, type ls. ls isn't working. But you know what? At least one command works. A broken clock is right twice a day. Okay, so we got a question. Error doesn't give receive how many child students work on your end. What kind of error are you getting? We're going to need a little more detail here. I don't have the ability to guess what error you're receiving. Now, obviously, I don't want you to send me your code. If you could give me an error message, I might recognize it and be able to talk about that error message. Fortunately, this right here is an unaddressable question. Okay, let's make this work for who am I and not for anything else. How do we do that? Well, we can compare this result, right? So we kind of need some sort of string compare function or a mem compare function, either one in this case. We can write a very simple implementation that works for things that are less than 8 bytes, because then we don't need a loop for our string compare implementation. What we can do is we can take offset input buffer and move that into, or take the first 8 bytes here and move that into, let's say, move that into RBX or even RAX. Why not? Who cares? Just be careful, make sure you're never inadvertently clobbering something, but we don't really care. So we'll say move RAX input buffer. I believe that syntax will work. We'll confirm. And then let's compare RAX with, does this syntax work? We'll see, because this is less than 8 bytes. I'm not sure if the assembler will be chill with that. Let's see. Make. No, it doesn't like that. What if I do single quotes? It's also not feeling that one. Well, we could make it real easy for ourselves. And we could put in yet another string here. Now you're going to see this style works-ish. Doesn't really scale very well. Let's go ahead and put who am I new line character. And we're just going to, how many bytes is this? This is, we're thinking about 8 bytes here. 1, 2, 3, 4, 5, 6, and then 7. And then maybe a null byte if we're lucky. Let's do this. Compare RAX with who am I? Does this work? Something generated. Then let's do jump not equal to loop, right? So if these things aren't equal to each other, just go back to the loop. Otherwise, we'll fall through and we'll write out hacker. So it'll like kind of work for one command. Who am I? Test. Huh? I mean, the rest of this doesn't really work so well. What the heck's going on here? Something's lagging, but you get the idea. Why is this falling apart? Who am I? Well, worked the first time. Who am I? Who am I? I think the issue is we overflowed that 8th byte, and it's no longer a null byte that we were relying on, so it doesn't work anymore. We wanted to deal with that because the issue here is we're doing like an 8-byte str compare, right? You would really want to implement str compare for this. What we need to do is null out that 8th byte ourselves. So what we can do is, and we'll make sure, well, I guess we know that this is 8 bytes. This is exactly 8 bytes because we got 1 byte, 2 byte, 3 byte, 4, 5, 6, 7, and there's also a null byte here. So this thing is definitely 8 bytes. This thing right here, well, there's a simple solution actually. Before we read, we can just set the first 8 bytes of input buffer to null, right? So we can just do move input buffer. Like we're just like, this is like writing bad code, but it works. And as long as we understand that it's bad, but it works, that's good. And we just say keyword pointer input buffer. So we null out the first 8 bytes, and now we're good to go for this implementation. Make clear test. Who am I? Now if I do this, and then I do who am I again, it works. And if the issue here now is if I do, well, I guess it's always a new line. I'm gonna say like what happens if I do that, but technically there's not a new line character here, so we're fine. All right, let's see here. Execve server blah 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 socket. So you're starting a socket, then you're binding to some port. Why is this thing there? How? Then you're listening on some port, except 43. Well, that doesn't look good. So it tells you right here, bad file descriptor. The trouble here is that I seem to be only getting this error. Only one getting this error. Well, okay, this error is telling you exactly what the problem is. So it says bad file descriptor. So let's actually even just pull this straight into VS Code. This is an strace log. This is an strace log that you could totally see in a whole bunch of contexts. How do I line wrap? Toggle word wrap. Cool. Okay, listen, accept this. Okay, so we start up our program. We created a socket. Again, this is the lecture slides tell you that this is the sequence to make. Except there's one little difference. Stream lagging? It might be lagging. There's a chance it's lagging, and I don't know what to do about that, unfortunately. So hopefully it stops. Okay, we'll assume that we're being understood and it's not lagging like a complete disaster. If we look at the slides say almost everything you did is correct, right? We did the socket, we got a 3. You did the socket, you got a 3. You do this bind, you got a 0. You did AF inet H2NS 80, 0, 0, 0, 16, 3. Look at all this. This all looks great. 16, we got our 3, we return 0, port 80, 0, 0, 0. Then we did a listen. Listen 3, 0. You got a 0. This is great. Boom. Then you got an error, -1 E bad F. The system call you made is not what the slides say to make. The slides say that you should accept 3 null null. You accepted 43 null null. 43 is not 3. So this is the issue. All of this is happening on your socket file descriptor, which is 3. That's why there's a 3 here, there's a 3 here. 43, not 3. This is not good. You need this to be a 3. Somewhere, somehow, you're overwriting RDI with 43 in some way. I mean, I'm not saying you necessarily have in your code. I mean, it's possible you have somewhere in your code that you did move RDI 43 and you literally just accidentally typed a 4 here. It's possible that's what you did. It's possible that somewhere in your logic, you're influencing RDI. And the way that you're influencing it, you're putting a 43. It looks like you got a typo of 4 here, though. That could be very believable. Maybe that's the simplest explanation. Does this make sense to the person receiving this error? This is not a good file descriptor. 43, you don't have 43 open. You need a file descriptor you have open. Technically, you could do like 0, or you could do 1, or you could do 2, or you could do 3, because these file descriptors are open. Now, 0, 1, and 2 are also going to, I don't know the error you're going to get. It might even be bad file descriptor there. Let's see. Man to accept. Error. What kind of errors can we get? I can even predict, let's see here, what kind of error that might be. E not sock. This is the error you will get if you put in a 0, a 1, or a 2. File descriptor, sock FD, does not refer to a socket. You put in 0, 1, or 2, you're going to get this. You put in 3, it's all going to work. It's going to be great. You put in another value, you're going to get E bad F, right? E bad F, E bad F. These error messages aren't lying to you. They're very informational. Sock FD is not an open file descriptor. You do not have 43 open. Well, we lost 43. Your message had 43. I have move RAX 43. Well, you also then have move RDI RAX, don't you? Like now I understand the issue. That makes sense. This is to be clear, this is a very common issue to be making this sort of mistake. This is why C is so nice. We don't have to do register management. You did move RAX 43 so that you can do an accept syscall, right? You did this and then you did this. The unfortunate issue is you also have this. Because at some point, you bind it. The result of socket came out through RAX, so it makes sense. So RAX came out, I want to put that into RDI. But here's the issue. You just messed with RAX. You can't do that anymore. RAX is no longer referring to your file descriptor you care about. It's referring to your system call number now. You need to save RAX into like R11 or something. I like this very clear. There's a good point. That yeah, this is definitely what's happening here. 43, the fact that it lines up, you are moving RAX into RDI. You can't do that if you're going to mess with RAX first. Like, technically, this would work. Though I also would question how this would work. It's, I guess, a little bit unclear. How did you manage to get this 3 in? And so the first one is easy because it's just right away. But if you're using RAX, I'm not actually sure how you would have gotten this to pass, unless you've hard-coded a 3 right here. As soon as you're done doing, so somewhere you have socket syscall, move RAX 41. one of the very first things you probably do in your code is move rx41, blah, 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 syscall. Right here, you need to do like move r11 rax. Just save this file descriptor, and now for this 3, get it from r11. For this 3, get it from r11. For this what should be 3, get it from r11. Assuming I don't think r11 is an issue to be messing with. You do have to be a little bit careful which register you use. The syscall instruction says RCX gets messed with. Oh, wait, don't do R11. Good thing I pointed this out. RCX gets modified by syscall and R11 gets modified. So change my mind on that one. Don't use R11. If you use, I don't know, I don't think we have anything that needs R10, right? R10 would be a 4th argument. I don't think you're making any syscalls that have a 4th argument. Maybe you are. I don't know, use an open register. Once I changed, yeah, R12 through R15 should be pretty safe. And if you really want to, if you're worried about registers, you could push it to the stack and then start grabbing it from the stack every time, but that might be a little unnecessary. Once changed to 42, it compiled finally, but still have some things wrong. Well, it depends on the S-trace, right? Just because you solved one issue doesn't mean you solved all issues. But yeah, your issue is this argument. However you're setting up RDI is just wrong, and it might be, I mean, truly the simple thing to do here is to, instead of doing this, just put a 3 in. Like, don't even mess with saving this thing. I'm telling you right now, you'll see it's always 3. Technically, that code's like a little bit worse because if for some reason you decided to open something before you did this whole sequence, then suddenly this would become a 4, this would be a 4, this would be a 4, this would be a 4. So it's technically like worse to just hard code these file descriptors, but I mean, it's going to work. You just have to manage that then. Cool. All right, hopefully that answers that question. All right, does anyone else have any questions about their challenge, like, you know, like an error message or something like that? Or something that doesn't make sense about one of these system calls? Okay, otherwise, while we're waiting to maybe see another question, we'll keep building our shell. Okay, we got our shell. We can type hello. We get a new prompt at least. We can type who am I? Hacker. Test, ls, nothing really works. Okay, the real way we want to do this is we want to write this program, and we don't want to deal with like implementing who am I also and just printing hacker. That's technically not a correct implementation of who am I. If I sudo su to root, right, and now I type who am I, well, not actually my shell. This would be incorrect, right? If I do sudo su roots and type who am I, it says root now, right? The who am I program doesn't just always say hacker. Okay. The way that we want to do this, turns out, is which who am I. There's a program. We can also just say bin who am I. This is a symlink to user bin who am I. Bin who am I. We just want to run this program. So if we want to do that, the way that we can do this, we can get rid of all this compare logic. This compare logic, we don't need it. Get rid of this write logic. Which one? Input buffer. I guess we already got rid of it. Right? Yeah. What we want to do is in front of our input buffer, just put like bin. We'll call this command. This is going to be a simple implementation. Now sitting in memory is going to be /bin, no null byte at the end, just these 4 bytes, because I didn't do .string. .string puts a null byte. This doesn't have a null byte, so 4 bytes, and then whatever the heck we type. So now what we need to do is we want to run. So first let's print it just to make it real clear. So we read in some input. Oh, I guess this needs to go. Well, we'll change it though. We'll say command. And so we're kind of abusing the fact that these are sitting next to each other in memory. Our command is the first 4 bytes, and then technically whatever is sitting in memory is whatever we read in, up to 1,000 bytes. They're just sitting next to each other in memory. It's very convenient. So let's go ahead and write out command, and we'll just write, we're not going to think too hard. We're just going to write 50 bytes. Offset command, 50 bytes, print it. Clear, make, test. I type in who am I? Well, looks like we had a bit of a bug. Maybe you saw that. You saw this was going to happen. We're missing a slash. We want another slash. No problem. Make, test, who am I? Cats. Well, we're printing 50 bytes, so that's why. Really, we want to print until a new line character and turn the new line character into a null byte and stuff. But it's close enough, right? We've got these things. And now we just want to run this thing. I guess if we want to be more correct here, the number of bytes we want to print is 3 for bin, 4, 5. So this is 5 bytes. And then however many bytes we read in. 5 plus however many bytes we read in is really how many bytes we want to write out. Because this will be however many bytes we read in, that's what we read in, plus 5 to get in our slash bin. So what we can do here is you could imagine doing move RAX, RDX, RAX, add RDX 5, right? This is what we want to do. Take the result of this thing, put it in RDX, add 5, we don't want this. And boom, it's going to work, right? Except no, we just talked about this, the previous person's error. We just clobbered RAX. We can't do this. This is no good. Now, this is a solvable problem, actually. It's really not that difficult. In this case, we can do this because we can do it right here. Now RAX is no longer safe. So if we ever want to refer to the length of this thing, at this point, we've lost it. I mean, technically, we still have 5 more than it. But as soon as we overwrite RAX, which was the return value of this syscall, it's gone. Right, we've clobbered it. This will work for our purposes right now, though. So let's just do that. And now we'll see that we don't get like this extra MI. So this MI is coming from who am I. If instead now we make it, we run it, we say who am I, we say ls, we say cat, we say test, we say that, right? This is just printing slash bin slash that thing. Okay. Looks like we got a bit of a discussion in the chat. Isn't it bad? So side tangent, we're kind of doing 2 things simultaneously, totally cool. Isn't it bad to hard code descriptor values like 3 in this case? I would like to know the answer to this too. I believe it depends on the order in which the binary opens files and whether or not it is predictable. So it is completely predictable and also bad. It's not, what does bad mean, right? It's kind of like you're writing unmaintainable code if you do this. If you start hard coding your file descriptors, here's what's going to happen. If I start my process, we'll just say execve, blah, 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 blah. My program starts. As we've said before, file descriptor 0, standard in, file descriptor 1, standard out, file descriptor 2, standard error. This is just like definitionally. But the reason that this is the case, and it's kind of a little bit annoying because VS Code's actually have a whole bunch of file descriptors, I think. Yeah. It's a little bit annoying because of VS Code. In fact, here's what we're going to do. I'm going to go here, here, iTerm, SSH Dojo. We're going to get out of VS Code for one brief moment just to make it a little bit easier for ourselves. And then we'll explain why VS Code is an issue. if I now look at proc self fd, well, in this case, it's kind of funny. We have 4 file descriptors open. The first 3 are pointing at dev pts, dev pts, dev pts, standard in, standard out, standard error. Literally just 2 means standard error, 1 means standard out, 0 means standard in. We have no idea what they're pointing at, but that's just what that means. Technically, ls has 3 open, and the reason it has 3 open is because it opened a file. That's how ls works. It opens up this directory. So it's a little bit clearer, I think, if we... So echo $$ is, this is the process ID of bash, this running shell. If I do ls proc that fd, well, technically bash also decides it likes a little bonus guy open 255. But 0, 1, and 2 are open. If I switch over into Python and I import OS and I do OS get PID, I have this process ID. We'll switch back over here and we'll do ls proc this thing fd. Okay, finally we got something that's more standard, right? 0, 1, 2, all pointing at this thing. This thing, truly, like if I say echo hello world and I write this over to dev pts2, this is totally valid. Guess what just appeared? Hello world. Echo, this really does work. Dev pts2. This thing can be written to. Okay. These things got inherited by from bash. Bash launched Python. Python is the child of bash. Bash had these things open. Guess what? Now Python has these things open. 0, 1, 2. If I open etc password, we now, if we look over here at this process, Python now has 0, 1, 2 open. The very next thing is 3. And we'll say f equals that thing. Okay, so we keep it open. Otherwise, Python will close it itself when it gets garbage collected and blah, 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 blah. f2 equals, let's open etc password again. It's not going to be 3 this time, though 3 will still be there. The next time we open it, it's on 4 now. And as you might expect, we do it again, it's on 5. Every single time you open a file, it's opening sequentially. It's just the next available file descriptor, that's what it's going to be. So when you say, is it bad to hard code 3? It's like yes and no. It's like truly every time you do this, it's going to be 3. It will always be 3. It's not unpredictable. There's some caveats to that, depending on how you start the program, because technically 0, 1, and 2 are there because our parent process had 0, 1, and 2 there. And so our child process just literally inherits these things. So if our parent process also had 3 open and set for inheritability, when we started up Python, we actually would have started at, we'd have 4, 5, and 6 currently pointing to etc password because 3 would have already been taken by being inherited from our parent. Now, default behavior is going to be that the only things that are getting inherited are 0, 1, and 2. But you can very easily change that to not be the case. You can make it so a different process gets inherited. So for example, if I do import, I guess we already have OS. Do we have OS? Yeah. If I do OS system ls proc self fd, these are now, like, etc password is not opened by ls, right? Because it's just not there. However, technically, if I look at f, and I'm going to have to remember how to modify this. OS, how do I change? There's this flag, so going deep dive here. Man to open. One of the things this thing talks about is this flag clo exec. Clo exec enable the close on exec flag for the new file descriptor. Specifying this flag permits a program to avoid additional F control F. I guess this is how we do it to set the FD close exec flag. Blah 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 blah. Does it actually not really say what it does? Oh, here. I guess this talks about it. Or does it? Maybe not. This initially. Okay, yeah, this. By default, the file descriptor is set to remain open across an execve, as in you start a new process. Or that's technically not correct, but you execve. I.e., the fd clo exec file descriptor flag described in fcontrol is initially disabled. The clo exec flag described below can be used to change this default. So this thing is whether or not we're going to inherit it. But clo exec means do we close this when we execve something or not for the purposes of that execve person. So by default in Python land, when Python is opening these things, it's specifying clo exec. Now, as it talks about, we have this F control thing. We can technically modify this with F set to. So the way this works is import F control. This is also just a syscall. F control dot F control. And we're talking about, let's say, file descriptor 3, because as a reminder, that's pointing at this etc password. Well, I guess it said F control dot F set FD. Hold on, what are the arguments to this thing? FD command arg, cool. So file descriptor 3, F set FD, F control, F. Does clo exec exist here? Or is this, it's probably os dot clo, os dot o clo exec. Yeah, I think that's what we want. So if I want it to be inherited, this is a long path here. Hopefully this is shining some light on the nuance of this thing once we finally get here. Clo exec. Well, we don't want clo exec is the issue. How do we... Skeptical about that one. Let's see here. Well, here's what we'll do. F, I think there's F get FD. What's the value of this? Well, maybe we're good. Let's see what the heck happens now. ls, we didn't get it. Python F control set clo exec. I'm wondering if the shell is also doing something. Import subprocess dot run bin ls al self fd. Okay, that's definitely fine then. What the heck is this F control thing? Okay, here's what we're gonna do. os.open. Open etc password again. This time we're not going to do it wrong though. os.open etc password. Okay. 0. Okay, so that gave us file descriptor 6. Is this going to show up now? Will I get my file descriptor 6? Nope. Oh, it's okay. The issue is Python just is so annoying. It does so many different things of trying to close these file descriptors because the default behavior, you just don't want to pass these file descriptors. I'm trying to think. Okay, let's just do it in bash, actually. ls-al proc self fd, right? We've got 0, 1, 2. I think we can say exec. The syntax for this. There's a syntax to, I don't know bash well enough. Bash syntax open file to file descriptor. There's a way that we can basically say open in bash and it ends up on a file descriptor. This. Well, that's close. Exec this wild syntax. Etsy password. What? Well, I guess probably that. Okay, and now, as a reminder, our bash process is now this guy, ls-al proc this guy fd, right? So file descriptor 3 is now pointing at Etsy password for our bash process. And we want to look at our ls process, so proc self being ls. Before, when we ran ls-al proc self fd, well, I guess we didn't see anything because there was nothing. But now we've got 3 open. If we look at this thing, 3 appears now in ls. The reason for that is because it's open in bash, and bash starts the ls process because we're not in Python, who just forces file descriptors to be closed when you execve, like very aggressive. There's a way to get around it. It's just we're not going in there. Under this circumstance, so it took a while to get there. Under this circumstance, if you now started your web server, file descriptor 3 is open. The next thing that's going to open, as we can see, ls opens a directory because that's how it figures out how to ls the directory. The next thing that opens is 4. Before, when we did it, right, the next thing that would open was 3. So proc this number fd would be on 3. Now it's on 4. If I open Etsy password again on 4 and on 5 and on 6, and I ls-al proc self fd, the next available file descriptor is 7. So this thing is going to be on 7. So you can't, for code maintenance purposes and for correctness purposes, technically, you can't refer to 3 and just say that 3 is going to be what I want. Except you kind of can, because like you're not going to do this, right? I mean, yeah. So someone was asking, can you drop the links for those resources you were referencing in different tabs? So this is one thing, very useful. This was another thing I was looking at, to look specifically at the syscall. I don't think this stuff really matters for you. This was, let's just quick Googling. So yeah, it's hard to say whether it's bad to hard code. It is. It's just bad code. But it's not wrong, I guess is what I would say. Maybe, like, it's semantically wrong, but it's not technically wrong. Okay, but what if it opens files non-deterministically? Then you can't be sure whether or not 3 corresponds to the file of interest. Putting standard FDs aside, 3 might be one file, 4 might be another. Past the original code might prevent close from being called outside. Yeah, it's dangerous. You can be technically correct, but you're not semantically correct, even if it lurks every time under normal circumstances. I don't know. Hopefully that long-winded rant provides some light on it. Ideally, you're not hard coding your FDs, because you'll run into subtle bugs when something does start going wrong that you're not expecting. It's easier to not hard code your file descriptors, with the exception of, as you said, 0, 1, and 2. Okay, any final questions? Otherwise, I'm going to wrap this up. I guess we didn't quite get to the end of building our shell. The next step, if for those curious, would be to call execve. All right, hold on. We'll do it real quick. So instead of write, so right now, we made this thing, we run this thing, ls, it shows ls. Okay. Instead of printing this thing, we want to execve this thing. Here's how we do this. Execve, we're going to have a little bit of an issue, actually. We're only going to be able to launch one program, as we'll see. We specify a file name, we specify argv, we specify envp, RDI, RSI, RDX. Syscall 59. So we'll deal with this here in a second, actually. This bit. What we want is syscall 59. RDI, we want to point at command, offset command, because that is our file name. I believe for argv, we don't really care. We can make them null pointers. I believe that's still true. I think we can just make these null pointers. It means we're not having any arguments, no envp. Just make them 0. I think this should work fine. This is slowly evolving with time, whether or not this is fine. We're going to say that hopefully that this works. Now, the only issue here is that file name needs to be null terminated. So we need to do this. So let's actually just add rex5. So 5 bytes further. This is the total length now. We want to write a single byte here, byte pointer, rex 0. We want to just put a nice little null byte here. I think this might be off by 1. I think this is right. Let's see what happens. Okay. Make test ls. So close. strace.test ls new line. So 5. I think we'll debug this in a second. My first guess is to make this a 4. Just feeling good about 4. Test ls. Nope. Not so good about 4. Okay, let's GDB this. Make gdb./test. Oops, gdb./test. We will start. Nope. Oops, actually we needed, well, hold on. gdb-q less output start start at the beginning. Bunch of instructions, set disassembly, flavor, Intel. I'm not using my normal class one. We're just using vanilla GDB. We're going to want to break right here. So where we're writing this null byte to rex, let's see what the heck is going on here. Continue there. We say ls. We are about to write a null byte to this location. What the heck is rex pointing to? 8. Oh, that doesn't sound good. Yeah, well, that makes sense, right? This is how many bytes we read. We added 5. Okay, well, this is no good. We need command. We want to do command plus 5. Or input buffer, just literally at the end of input buffer. So what we want is, let's see if this syntax works. We want to do command plus rex. We'll see. I'm not so sure if this syntax is going to work. We want this to be a null pointer. We're allowed, right? However many bytes, actually not command, we want input buffer. Input buffer plus however many bytes we read. So we read 1 byte, that would be just a null byte. So -1 technically. We'll see if the syntax is supported. Otherwise, we'll make it work. Make. Something happened. Boom. Okay, we just did it. I'm actually really surprised that syntax is supported. It's very nice that it is supported. Input buffer plus however many bytes we just read, -1, because we want to go back and overwrite the new line character with a null byte, right? If we type in ls, technically it's ls new line, so this would be 2, 3. We want to go back 1. We want to overwrite this guy with a null byte. Cool. But we only get one command for our shell because execve consumes the process. This is where fork would come in if we wanted to do multiple things. What we would do is we'd fork first. Okay. Anyways, we're not going to keep doing that for now. We're going to say that's good to go. Thank you all for attending, and good luck on the module. Feel free to ask further questions in the Discord or a timed recitation. Goodbye.